with relatives who got the Rona. And obviously, number one, I don't want to get sick, have anything bad happen. Number two, I don't want to miss work and have to use up all my vacation or sick time for just being like quarantined. Because that's crappy. So hopefully everything goes good. I think they're not gonna like it, and they'll probably talk crap about us when they leave. But I think we're spending as much time as possible outside on the back porch, and even when we're inside, I think I'm gonna wear a mask in my own home, my relatives here, because I think that's where we're at now. So just be cautious if you don't want to get quarantined or get sick. Make sure you keep your mask up around people, and you know what? Who cares what other people think? Uh, it's all about you and yours, and not letting anybody dull your sparkle. So, um, just a reminder: the 7 and 8 homeworks are up, and we will have the 7 and 8 test Monday. So come prepared Monday early morning for the test. I will have that ready to go for us, and the Monday we get back from Thanksgiving break, we're going to have the chapter 9 and 10 tests, which we just finished lecturing over yesterday. We finished chapter 9 earlier, but we finished chapter 10 yesterday. The homeworks are already up. So if over the Thanksgiving break you're quarantined inside your house and are looking for stuff to do, you can go ahead and get an early jump on that. When we get back from Thanksgiving, well, actually, as of the end of the day today, we'll have 3 weeks left. And so we're going to go through these last 4 chapters pretty quickly. Not super in depth. It's all kind of on the same stuff. It's on atmosphere and weather. And the weather stuff, I will go through the PowerPoint pretty quickly, but we're going to do a signature assignment that kind of covers the weather stuff a little bit more in depth than just the lecture. Yeah. I don't know if we'll end up doing we did the plate tectonics. Did we do the earthquakes one? We did the plate tectonics lab. Maybe we'll save the earthquakes lab for next semester. Because I don't know, they have a lot of labs for next semester. So we'll probably save that for next semester. I need to see if I can buy that lab manual and maybe make copies out of that. We'll see how that goes. But anyways, or like I mentioned to the other class, we might try a different type of book next semester. It'll cost a little bit more, but it'll have more digital content and more interactive stuff for y'all to use. And y'all might be my guinea pig class because you'll get one cheap semester and then one not cheap semester. And I think it'll be better because I think we'll have more interactive stuff to do, so I won't have to stand up here and lecture like every single day, which objectively is not the best way to learn. But let's be honest. If I told y'all to read every single chapter, it wouldn't happen the majority of the time. So it is what it is, and I do like talking about geology, and it's kind of what I get paid to do. So lectures it is. So with that said, let's go ahead and get going on the next lecture, which is the atmosphere. We're starting with the atmosphere and how we heat the atmosphere. And actually, let me go ahead and fix my PowerPoint real quick. Next year, I believe I'll have all these saved, so it won't be a big deal. Set up slideshow. Okay. Save it. Bing, bang, boom. Now we're done. Full screen. All right. So we're starting in the atmosphere. We actually have 4 chapters of atmosphere, which is, I don't know. I think it's a little ridiculous for a geology class, but that's just my opinion. And obviously, this is how it goes. So we're going to talk about the atmosphere for the last couple weeks of the semester. Not like we haven't spent plenty of time talking about the Earth itself and space and all the other interesting things, but if you ask me, the atmosphere is a little bit dull. And yeah, there's lots of stuff going on, and it's important because of the weather and everything, but I'd rather talk about the rocks. So, yeah, you're going to have 4 chapters about atmosphere and not a single chapter that really goes into depth about fossils or the study of fossils and past life forms. Come on, come on. So y'all are probably familiar with these two terms. Weather is going to be your short-term description of temperature and humidity and precipitation. It occurs over a short period of time and it's constantly changing. Like afternoon when we leave out of school, it'll feel great outside. Overnight, it gets down pretty cold. That's your weather. Climate is an average taken over a long period of time. Climates are generalized. It's going to include all the different weather that you get on a short-term basis and kind of smooth everything out. That being said, climates can also change too. One of the things that struck me when I went to master's school and did my master's over a oil field that's in the Middle East is you learn the history of the rocks that are in the Middle East, and it for a very, very long time was not a desert, arid environment. It was down in the tropics. It had lots of tropical features in it, which is actually where the oil and gas form. Oil and gas are from biological buildup over time, not dinosaur bones, but old plants and different offshore high biological sites. And so that's not really something that occurs in desert areas. You do have life in deserts, but not by any means a lot of life. And so for the Middle East to have that much oil and gas, which is really an immense amount, it had to be in a very tropical climate for quite a while. So now their continent has moved. All the continents have kind of moved. Weather patterns changed, and they're in a very arid, dry climate. So elements of weather and climate, what adds to your weather, what adds to your climate. Properties that we measure regularly are here: temperature, humidity, cloudiness, precipitation, air pressure, wind speed, and direction. Hello? Yes, he's in here. Yeah, no problem. Yeah, we're just doing a lecture. All right. All right, no problem. Grant, Miss Jones wants to see. Okay, so they got a little chart here to go along with that. The chart at the bottom has months, January through December, and then it has temperatures on the right in Fahrenheit, temperatures on the left in Celsius, and you can see that during the summer months we have our high temperatures. To be fair, this doesn't tell you where this graph is taken. It's not in the southern hemisphere, because the southern hemisphere, their summer comes in our winter months. Which, if you haven't enjoyed the interesting Australian Christmas, Australians have their Christmas on December 25th, the same as we do, but it's like the peak of summertime there, and so it's like hot death outside, and they're like doing the Christmas thing, which is hilarious. Uh, Also, just on a side note, I love the jokes. Like, there's internet memes about basically how Australians are on the bottom of the earth and they would just fall off if they didn't have their like harness, like tethering them to the bottom of the earth. And then like some Australian will pull out his boomerang and like hit their harness and it comes unhooked and they just fall off. Uh, I know it's like childish and stupid, but I love those memes. They're the greatest. So okay, air is a mixture of discrete gases. They mean discrete in that you cannot see the different stuff that's in the air. If all of a sudden the oxygen level increased in the air, you might be able to tell based on how you feel, because oxygen is going to make you feel a little bit lightheaded, but it's not something you can see. You can't see all the nitrogen in the air, all the oxygen. Know that our atmosphere is 78% nitrogen, so the vast majority of it's nitrogen. Um, if you add in oxygen, you get up to what, like 99% of the atmosphere. So nitrogen and oxygen is well above the only two ingredients in the air. Nitrogen is inert, so when we breathe it, it doesn't really do anything for us. We just breathe it in and breathe it out. Um, it's not really going to combine with anything else. It's just kind of an inert gas. Uh, Argon and other gases are also in there. Argon is obviously a noble gas, and so it's also inert and doesn't really combine with anything. And then 0.03% of the atmosphere is carbon dioxide. That level does change depending on what's going on in the earth, what kind of volcanic activity you have, how much plant matter and activity you have. And so carbon dioxide is a greenhouse gas. As we do more and more studies, they're also starting to, I don't know if it's on this chart. Yep, there it is. Methane, CH4, is also a greenhouse gas. And even though there's a lot less methane in the atmosphere, they're starting to understand that methane is such a bigger factor in the greenhouse effect that even though it has a smaller amount, the fluctuations in methane as a greenhouse gas can outweigh the fluctuations of carbon dioxide as a greenhouse gas. We're not going to talk about that a lot, or really kind of go after methane in the same way that we go after carbon dioxide, because methane is largely a byproduct of, well, not largely, but a huge output of methane in this country is going to be the oil and gas industry. And when you go after the oil and gas industry, in a way, you go after people's jobs, and it's never plays well politically. With carbon dioxide, you can go after big companies and their profits, and that seems to play a little bit better with everybody. But methane is a big deal. And although, yes, cows do produce it in their farts, it's not enough to generally change the amount of methane. That being said, you should all eat different cuts of beef. If you're just like a ribeye person, know that there's only a certain amount of ribeyes in the cow, and then everything else also has to be eaten, or it's going to get thrown away and be wasted. We waste a lot of food in this country. But that being said, I think my in-laws are bringing ribeyes over to grill. So don't let me like influence you and make you think that I'm perfect, because I'm not. But let's see. Variable components of air. What changes depending on where you're at and the time of day or the time of year? Water vapor can be up to 4% of the air's volume. If it gets concentrated enough, it can form clouds and precipitation. Water vapor is also a greenhouse gas. It helps reflect the solar energy and keep it from leaving the atmosphere. Aerosols are going to be tiny solid and liquid particles. Water vapor can condense on these aerosol solids. They reflect sunlight. They also color the sunrise and the sunset. And we've had to kind of limit certain aerosols to try to prevent more global warming and try to prevent the depletion of the ozone layer. Y'all are probably too young, but when I was younger, there was a big talk about CFCs. It's like carbon fluoride, something else. And it was a chemical that they used in like hairspray or any kind of like spray cans had CFCs in it. And then they figured out that CFCs like combined really, really well with ozone. And so it's depleting the ozone layer and causing a lot of problems. And then when people started to ask questions about it and we started to be concerned about it as a people, and our politicians started to be concerned about it, they started asking questions, and the industry's like, yeah, like we don't have to use that chemical. It really doesn't do anything for. It's just a chemical we put in there. And so they started to not use it, and the ozone layer has had several holes that have repaired themselves, and is generally in much better condition now than it was like 20 or 30 years ago. On a little side note of chemicals that we don't really have to use, especially for ladies, parabens are apparently really bad and in everything. Parabens. It's like a preservative they use to keep the product good on the shelves for longer. And they've just defaulted to like everyone using parabens. Well, now they're getting better at companies not using them. There's so many companies that just don't care. They're like, I'm going to put whatever I can that's cheap in there, and people are going to buy it, and no one's going to complain all that much. And if the small group of people who are somewhat concerned about their health don't buy my product, I'll still make millions and millions of dollars. But they started to, people that are kind of proactive are asking these companies, hey, can you use something else than parabens? They're like, yeah, it's not going to change our product at all. Like we could use something different. And so companies have, but you start to find out that, yeah, we just put this chemical in here to do one thing. And we really could use anything else, but we just didn't. And then they found out that parabens were probably not doing good things for women and their reproductive systems, and we're starting to try to avoid those. But you got to read the labels. You got to read the labels on the back and see what's in there. And sometimes they only have one paraben. Sometimes they have all three. They're like, yeah, we're just going to put all the parabens in there. That's just how we're going to go. We try to at least be aware of things. You can't avoid everything all the time, but do be aware of the stuff that you're putting on your skin and in your body, and what the possible consequences might be down the road. Let's see. So, variable components of the air, ozone, and I just mentioned the ozone and CFCs. Look, I didn't even know that was going to be there. I haven't seen this PowerPoint in a year. But yeah, CFCs were depleting the ozone layer, and then we all got together and we're like, you can't use CFCs anymore, and they stopped using them, and now the ozone is in a much better condition than it was. Know that ozone is O3. It's just like the O2 that we breathe, but it has an extra oxygen, which makes it not good for us when you have ozone layers and the ozone layers or ozone days. And either the ozone is weak up above us, or I believe, and I may be wrong, so I'm going to put an asterisk next to this. Asterisk. I believe there's days when the ozone layer kind of comes down, and there's a risk of you breathing in more ozone. Maybe I'm wrong about that. It just sounds so wrong. But I feel that I've heard that before. I don't know. So the distribution is not uniform. It blows around like with the rest of the atmosphere. But in general, we have this nice layer of ozone up above us that helps absorb UV radiation from the sun and kind of protect us from that. So it's about 10 to 50 kilometers above the surface. But like I said, I think it varies depending on where you're at. And if it comes a little bit lower, it can kind of be bad for your breathing. So this is a picture of the ozone layer. You have your high stuff in reds and yellows and greens. You have your low stuff down in blues. And so you can see at the poles, we don't have a lot of ozone up there. To be fair, don't really need a lot of ozone up there. You're not getting direct sunlight at the poles. It's more at the tropics and at the equator that you're getting more direct sunlight. So, and obviously there's not a lot of pollution going on at the poles. So it's not like these holes in the ozone layer are from us and what we're doing. It's probably just more of a natural thing. But what is this? Extent of ozone hole. What is this map? We have years, we have millions of square kilometers, and millions of square kilometers of what? Of ozone hole? Area of North America, area of Antarctica, extent. Yes. So I guess the whole red line, not just that part of the red line, is the extent of the ozone hole. So you can see in 1980, when we first started measuring it, they have it down here at 0, and then it comes all the way up very quickly. Around 1990, 1995, 2000, you kind of reach your peak where it's about the size of North America. And then, it comes down sharply here. I don't know what, that seems like an outlier because it comes down way sharp and then goes way back up. But anyways, it kind of stays up here, and you can see we are on a downward trend now. This is not an updated map. So I wonder where it's at currently, but I believe we're doing a lot better now that we've cut out the CFCs and allowed it to kind of repair itself a little bit. So atmospheric pressure. Atmospheric pressure is the idea that when we're standing down here at the surface of the earth, you essentially have a whole atmosphere above you being pulled down by gravity. Air doesn't weigh a lot, but it does give pressure to you and your body. And if that pressure were to go away, like if you were out in space, in the vacuum of space, that would be bad for you. Your body is designed and has evolved to be under that pressure of the atmosphere. And so even going up to a mountain, at the top of a mountain, you're going to have a lot less pressure than you have. I believe on an airplane, when you have your ears pop, I believe it's the opposite. So the airplane does go up into lower pressure areas, but the cabin is pressurized. And I think in airplanes, the cabin is over pressurized. It's also more of like a structural thing. If you have an empty soda can, you can crush it very easily. If you have a full soda can, it's rigid. Like you can stand on a full soda can and it will support your weight. And so I think when your ears pop on an airplane, it's more because it's slightly over pressurized than under pressurized. But if you like every year, if you're a Cowboys fan, you watch them play. They don't play them every year, but every once in a while they go into Denver and play the Broncos in Mile High Stadium. And the players who aren't used to playing there have a real tough time breathing. You'll see them on the bench, like huffing oxygen, because just being up 1 mile causes you to, there's less air. There's literally less air up there. And so every breath you take, you're getting slightly less oxygen than your lungs are used to. There's people that live up high in high elevations on mountains, and their body has developed, and this isn't necessarily a heredity thing. You can train yourself to do this. Their body has developed to pull more oxygen in per breath, and so they can live at those high altitudes and do stuff. If you were to go and like move up to a high altitude place, it would take you several months for your body to start to pull in more oxygen and kind of get used to that. In fact, that's one of the reasons why people who try to summit tall mountains like Everest, they spend so much time at these different base camps, not just waiting for the weather. Often you are waiting for the weather, but why wouldn't you just show up a week before and wait for the weather to clear? Why do you show up like a month or 2 months before? Because they get them up in these higher elevations and you get your lungs used to breathing that lower oxygen content air. And so when it comes time to go all the way up there, you're not just like exhausted and falling out because they'll leave you behind. They're not going to drag you down the mountain. So yeah, up at Everest, you have what's hold on. Oh, millibars. We're measuring millibars. So there's actually lots of different ways you can measure atmospheric pressure. We kind of went over this in chemistry when we talked about gases and pressure and volume and temperature with gases. And 1 atmosphere is how much you have at sea level. So that's just like a standard, easy math kind of thing. Average sea level pressure in millibars is 1,000 millibars or 14.7 psi. Psi is what we put in our tires. So in a tire, you have what, like 32 to 40 psi. So much higher than your standard atmospheric pressure. So pressure decreases with altitude. The higher up you get, the less air you have pushing down on you, and you have less pressure there. So half of the atmosphere is below 3.5 miles. 90% of the atmosphere is below 10 miles. So you go like any appreciable amount up, and you're really, really running out of air to breathe up there. So atmospheric layers based on temperature. We're going to start with the layers. So the bottom layer that we live in is called the troposphere. I always remember this because troposphere, maybe I should, someone Google what trope means, or I don't know, troposphere. Google troposphere and see if it gives you like the root of the word or what specifically tropo means or trope means. So I think if you Google trope or trop, you're gonna get like a trope in literature, like a theme that people kind of follow.
Greek. It's tropos.
What's it stand for?
A turning.
A turning? Okay. All right. Well, that doesn't help me. But the way I always remembered it, which I knew was wrong, but it helps me remember things. Troposphere is like tropical to me, and the tropical stuff is going to be down in the lower layer, and so it's not like the most intelligent way to remember it, but it's always the way I remembered it. Troposphere is tropical, and the tropical stuff is on the surface. And so the troposphere is the bottom layer where we live on the surface. So it is the bottom layer. The temperature decreases with altitude, so your temperature is going to drop the higher you get. And that makes sense because basically everything that we live on, including the mountains, are in the troposphere. And as you go up higher in elevation, it's going to get colder and colder, which is why there's snow on the top of the mountains and not snow at the bottom, because your temperature decreases the higher up you go. There's an environmental lapse rate, which is an average of 6.5 degrees Celsius per kilometer that you go up, or 3.5 degrees Fahrenheit per 1,000 feet. So every 1,000 feet you go up, the temperature drops another 3 degrees on average. The thickness of the troposphere varies, but the average height is about 12 kilometers. And so if you go back here, the height of Mount Everest, which is the highest mountain above sea level, is just over 8 kilometers. So you're well within the troposphere at the average height of about 12. So the troposphere has most of our air, and it's where we live and kind of do most of our stuff, except for fly planes. And then for each of these layers, the top of that layer where it stops is going to have the beginning of the name, like troposphere, tropo, and then you're going to have pause. So instead of sphere, we put pause. So on the next one, when we go to stratosphere, you're going to have the stratopause. Where the mesosphere ends, you have the mesopause. Where the thermosphere ends, you have the thermopause. And so each of those little layers, not little layers, but each of the layers ends with a pause of that name. Let me go back because they had some pictures of the stratosphere. So in the stratosphere, you have all your mountains, all your tropicals, in the troposphere, you have all your mountains, all your tropical stuff, all the land, basically the surface of the earth. So how do we measure the temperature change, the environmental lapse rate? It's measured with a radiosonde, and they attach it to a weather balloon and let the weather balloons go up and record all the information. When they get high enough, you have less atmosphere to kind of push in, less atmospheric pressure to hold the balloon in. So as the balloon goes up, it just gets bigger and bigger and bigger and bigger. And then at a certain point, what will a balloon do if you kind of overinflate it? Yeah, it'll pop. And so these are designed to go up to a certain level and then pop. And when it pops, the equipment falls back to the ground and they go and retrieve it. I believe they go and retrieve it. That would be really wasteful if they didn't, but I'm pretty sure they do. So they attach it to a balloon and it transmits data by radio. Hopefully they go and retrieve it, and they're just leaving it trash all over the place. So this is a map that kind of goes through the rest of them. The stratosphere is above the troposphere. This is where we fly planes. This is also where the ozone layer is. And also one of the other things is the temperature increases in the stratosphere. So know that in our little area of the world down at the bottom, the temperature decreases as you go up. It just gets colder and colder and colder as you go up the mountain. But you can see the temperature line here. It zigs back and forth as you go up towards space. And it's not always going down. There are warmer parts of the atmosphere than kind of up at the top of Mount Everest. So the stratosphere is about 12 to 50 kilometers thick. It's pretty thick. The temperature increases at the top, and the outer boundary is called the stratopause. The mesosphere is next. So you have troposphere, stratosphere, meso. Meso means middle. And so 50 to 80 kilometers thick. The temperature decreases again in the mesosphere. You can see it coming down. The outer boundary is the mesopause. And in the mesosphere, if you see shooting stars, they're usually burning up in the mesosphere. There's not very much atmosphere up here in the thermopause. There's not a lot of atoms. So you're not really getting that friction and heating up of a space debris until it gets down towards the bottom of the thermosphere and into the mesosphere. So when you see shooting stars, they're generally in this kind of part of our atmosphere. Yes, and then we go to the thermosphere. Thermo obviously means heat, and so during this section of the atmosphere, you're going to be heating up again. It doesn't have a well-defined upper limit, but I will tell you depending on what book you're reading, and I don't know that they mentioned this in your book. You have the book open, right? Did they talk about the exosphere?
This is an economics book.
Oh, that's fine. Don't feel ashamed. But I don't know if in this book it talks about the exosphere or not, but there is another layer above the thermosphere that they call the exosphere. And it's kind of like the boundary between the thermosphere and space, where we really run out of atmosphere. So there is no well-defined upper limit, but there is a limit somewhere, and we do have another layer on top of that we recognize today. Like I said, your meteors aren't really burning up in this part of the atmosphere because there's really just not much air. It's only a fraction of the atmosphere's mass. You're not really getting a lot of friction going on there. That being said, because there's so few atoms and it is so kind of empty up there, the atoms that are up there are moving very quickly. They get a lot of energy from the sun, and so they're moving at high speeds. And like we learned in chemistry, the faster your atoms are moving, the higher your temperature is technically. And so that's why the thermosphere, you see things heating up. Also in the thermosphere, if you're up towards the North Pole or the South Pole, you will see the auroras in the night sky. Those are happening in the thermosphere because they're right at the top of the atmosphere, kind of interacting with the magnetosphere. Lots of sphere words. So Earth's motions, how we rotate on a daily basis, how we revolve around the sun, and what that means for our season. So remember that the Earth rotates on its axis. So what we get when we get a day-night cycle is rotation. Revolving is moving around a central point in a circular manner instead of rotating on your axis. And so rotations give us days and nights. Revolving around the sun gives us years and our seasons. The seasons are caused by Earth having a tilted orientation. So we have a tilted orientation of 23.5 degrees. And that means during the summertime, especially here in Texas, the sun is coming like more directly at us. In fact, I don't know if it happens too much here, but there's some places I believe in Texas. Nah, maybe you'd have to be further down, maybe like in Hawaii or some parts of Mexico, because you can see the line here that they're pointing to. Not that this is 100% accurate, but you can see the line here that they're pointing to, and it's down below like the tip of Florida and probably the tip of Texas. What, 23.5 degrees? Let me see if I can see this on the map here. They should have this line marked. Is it the Tropic of Cancer? I think it is. 15, 30. I think that's what it's going to be. I think it's going to be the tropics. So the Tropic of Cancer, like if during the peak of summer, which I guess would be what is it called? It's what's when you have the longest days of summer? It's not the equinox. No, the equinox is equal. Yes, the solstice, the summer solstice versus the winter solstice, and then you have spring and autumnal equinoxes. So in the summer solstice, if you're standing on the Tropic of Cancer, which is in the northern hemisphere and comes like just south of Florida, it kind of runs in between Cuba and Florida and through Mexico and really close to Hawaii. So I think the picture I saw was in Hawaii. But you can stand and like your shadow will be going straight down. Like it won't be out to the side in any way whatsoever. So I think somebody had taken a picture. This sounds dumb, but they had taken a picture of one of the poles, like at a 7-Eleven that keeps people from like driving into the store. But it was daylight outside, and the pole had no shadow because there was no overhang. It was just like a straight up and down pole. But it like melts your brain a little bit to see a picture of something that has no shadow because everything should have a shadow. But it's because it was really close to the summer solstice and the sun was literally directly above head at the time. You can get that at the equinoxes if you're standing on the equator. The sun will be directly above you. And so they kind of show that here. And the equinoxes are the time of year when everyone on the planet gets equal amounts of day and nighttime. You have 12 hours a day, 12 hours a night. Doesn't matter what latitude you're at. That's your time frame for day and night. Doesn't mean the sun is completely overhead for you. That's only going to happen if you're at the equator. But at that point in time, everything is kind of lined up. And let's see, the direction the sun is kind of perpendicular to the inclination of the pole. And so it doesn't matter that the poles are inclined. You're getting 12 hours a day and 12 hours a night. So that's the equinox. And then at the solstices, summer solstice, obviously for us, you get your longest days and your shortest nights. And then winter solstice, you get your shortest days and your longest nights, which is why it's colder and you have the sun at a higher angle, so you're not really getting as much direct sunlight. Let's see. The winter solstice is going to be December 21st or 22nd, depending on kind of what year and what's happening. Yeah, nice. I like that. So we're still about a month away, a little bit over a month away from the solstice, when the days will be the shortest, and it'll still. We already did daylight savings, and now it's light when we get here. I wonder if by the time the summer solstice comes, it'll start to be getting dark again when we get up to go to school. I don't know about y'all, but when I leave the house, it's the sun's starting to come up. It's more light, yeah. So this just gives you another image of kind of the differences in the sun's motion depending on the time of the year. So the summer solstice, if you're at 40 degrees north latitude, which 40 degrees north latitude is, there's 30, there's 45. So 40 degrees north latitude is going to be, that's going to be probably like Kansas, Nebraska kind of level. So we're probably closer down towards 35 maybe in the Dallas-Fort Worth area. But still not too bad from us. So the summer solstice at 40 degrees north latitude. It's the longest day of the year. It's about June 21st to June 22nd. And notice that the sun is not directly overhead if you're at this latitude. You're further north than the Tropic of Cancer, and so you will have a tiny little shadow there, probably your smallest shadow of the year. As spring, I guess they're going backwards, spring or fall. So let's go forward into fall. So at the fall equinox, you have day and night is equal, 12 hours of each. Your shadow's a little bit longer because the sun's at a further angle, which also is what helps make it cooler. And then winter solstice at 40 degrees north latitude, the sun is further down on the horizon here, and it's going to be your shortest day. And a little side note, I don't remember ever having this problem. The last 2 days, in 8th period, the sun beams through that window, and the person who sits 2 desks behind where Andrew's sitting right now has this like bright sunlight beam directing right on their computer, and you can't even really see anything on your Chromebook. And so I've been having to like pull the bookshelf over and stack my backpack on the bookshelf to kind of block out the sun so they can actually do their work. All right. So just to show you also, that is what more directly affects our temperature than the time of sunlight that you get. Like obviously in the summer, we get the most hours of sunlight day. It's not that we get more hours of sun, it's the angle the sun is coming. In summertime, we're getting this direct vertical angle, which is going to give us more of that energy. The more inclined your angle is, you're going to get less of that energy. And we can see that because at the poles. At the poles, they're still getting a decent amount of sunlight. In fact, there's times at the poles, if you're above the Arctic Circle during the summer, the sun never sets. It's daylight 24 hours a day for like a couple months. And it's the opposite. In winter, the sun never rises. It's dark for like 24 hours a day for several months. but you're not going to get warm there, even though the sun's up all the time, because your angle is so severe. You're not getting that direct sunlight. It just kind of comes up above the horizon and goes down a little bit lower. Have y'all ever seen that movie? What's it called? I don't remember the name of it now. But basically, they're like, I want to make a vampire movie, but I want to make it. Yeah. What?
I watched that the other night.
Oh, but you don't remember the name?
It's.
I want to say it might be like 40 Night. I don't know if it has a
30
name.
30 Days of Night or something.
30 Days of Night or something. Yeah. So basically, they're like, I want to make a vampire movie, but the vampires like run roughshod over this town that's in the Arctic Circle, and the sun never sets. So like they come out when wintertime comes and the sun sets, and they have like a whole month of these vampires like trying to get them. I don't know why they chose to be Arctic vampires. I guess so they could have that month-long kind of thing. But that's a pretty scary movie.
I thought it was good.
Yeah. All right, have a nice